Hey, now we're going to start talking about fluids. Fluids are any type of liquid or gas. Gas is also considered a fluid. Fluids are something that flow and take the shape of their container. Um, so our objectives: calculate the density of an object, determine whether an object will float based on density, and calculate the force on partially or fully submerged objects using Archimedes' principle. Now, density, we usually use in physics, we usually use the lowercase rho, which kind of looks like a P, is the ratio of an object's mass to volume. Less dense fluids float on more dense objects, and less dense solids float on more dense liquids. So in other words, I can float something on a liquid. If I float it on mercury, for example, which is a fairly dense liquid, I can float solids on top of that. I can take solids like corks and float those on a more dense liquid. Things float because of density. Now, a kilogram of water fills a cube 0.1 meter on each side. That's true. So if you take 10 centimeter by 10 centimeter by 10 centimeter cube of water, it will weigh exactly 1 kilogram. So density is equal to mass divided by volume. So it's 1 kilogram divided by 0.1 meter cubed, which is 1,000 kilograms per meter cubed. So if I had a cubic meter of water, 1 meter by 1 meter by 1 meter, it would have a mass of 1,000 kilograms. Remember, a meter cubed is pretty big. 1,000 kilograms is also pretty big. Water is heavy. Now, seawater is actually heavier. It's 1,025 kilogram meters cubed. Why is it heavier? It's got salt in it. So it's actually easier to float in seawater because the density is higher. Gold has a density of 19,320 kilograms per meter cubed. What will the volume of a single kilogram of gold occupy? So at 19,320 kilograms per meter cubed, that's a lot. Gold is extremely dense, one of the densest things we know. Think about water was only 1,000 kilograms per meter cubed. So density is equal to mass divided by volume, so therefore volume is equal to mass divided by density. So 1 kilogram divided by 19,320 kilograms per meter cubed, 0.00052 meters cubed. That's not very much. 52 centimeters cubed. 52 milliliters of gold is a kilogram. Gold is extremely heavy, so whenever you watch a movie and they're stealing bars of gold, realize bars of gold are extremely heavy. Now, fresh water has a density of 1,000 kilogram per meter cubed. Which of the following will float on fresh water? So again, remember that, the 1,000 kilogram meters cubed. So therefore, ice will float on the water. The reason it floats, 917 kilograms per meter cubed. Now I look at the other ones. Corks will also float, 250 kilograms per meter cubed. Magnesium will sink. Glycerol will sink. Even though it's a liquid, it will still sink because it has a density greater than the density of fresh water. Now, buoyancy. Buoyancy is that naturally feeling upward force you feel when you get in a swimming pool or in the ocean. You get buoyancy from air, but it's so small that we don't necessarily know it, and we've always dealt with it. And we don't always deal with being in the water, so we clearly feel it when we go in a swimming pool. Buoyancy is a force exerted by a fluid on an object opposing the object's weight. The buoyant force can be determined using Archimedes' principle. Archimedes' principle says the buoyant force is equal to the density of the fluid times the volume displaced times g. Now, in reality, the buoyant force is nothing more than the weight of the displaced fluid. So in other words, however much fluid has been displaced, that's the buoyant force on an object. Now, if you think about it, all we've really doing is taking the mass of the fluid times g. The mass of the fluid would be the density of the fluid times the volume. So what we're really doing is we're just saying F is equal to m times g. But when we're talking about buoyancy, it's the mass of the fluid that's important. Now, when objects float, floating gives us a kind of a guidelines, gives us a head start. What forces balance weight for an object that floats? Well, the buoyant force equals the weight for any object that's floating. So it really doesn't matter how much of it's sunk down into the water. If it's floating, we know the forces on it are balanced. It's not accelerating. So therefore the buoyant force up has to equal the weight force going down. Now, if the weight force wins, the object's going to sink. If the buoyant force wins, the object will pop out of the water. One place we see that, if you take a beach ball or something like that and push it down under the water and let it go, the buoyant force is going to win and the object's going to pop out of the water. If it's a tie and floating, the buoyant force is equal to the weight. So, what is the buoyant force on a 0.3 meter cubed box which is fully submerged in fresh water? So we start by writing down our formula. Buoyant force is equal to the density of fluid times volume times g. Remember, it's really nothing more than the mass of the fluid times g. Now, the density of the fluid, well, it's fresh water, so it's 1,000 kilograms per meter cubed. We know the volume is 0.3 meters cubed, and of course we know g is 10 meters per second squared. Again, you can use 9.8 if you want. I'm okay with that either way. Put all those together, you have 3,000 kilogram meters per second squared, and of course we know that 3,000 kilogram meters per second squared is 3,000 newtons. So there's 3,000 newtons acting on that box. Now, a steel cable holds a 120 kilogram shark 3 meters below the surface of salt water, and they give you the density of salt water is 1,025. If the volume of the shark is 0.1 meter cubed, what is the tension in the cable? So now, it's a force thing, so let's go back all the way back to the beginning of the course. Let's draw a free body diagram. Even though we're talking about fluids now, we're talking about forces, so it's really, free body diagrams are helpful. So we have there's our shark. We know it has weight acting down. We know that it has the tension of the cable coming up and the buoyant force coming up. Now, I guess the direction of the tension in the cable. I guess that the tension was pushing the shark up or holding the shark up. If I get a negative value, I just guessed wrong. But you have to take a guess either one way or another. Now, we know that, and I'm going to say the upward direction is positive, we know that the sum of the forces equal to 0. Newton's first law, there's no unbalanced force on the object. So now, I'm going to say that the force buoyant plus the tension force, those are my two upwards, minus Fg is equal to 0. Now let's figure out what each one of those are. So rearrange for tension. I get tension is equal to force G minus force B. So in other words, the force of gravity minus the buoyant force. And again, if it comes out to a negative value, I just guessed wrong. So my arrow would go in the other direction. So we know the force of gravity, 120 kilograms times 10 meters per second squared, 1,200 newtons, minus the buoyant force, which is the density of the fluid, times the volume, times g. 1,025 is the density, 0.1 meter cubed is the volume, and 10 meters per second squared. So I get 1,200 newtons minus 1,025 newtons. So I have 175 newtons worth of tension in the cable. Since it's positive, I guessed right. A hollow rectangular boat of concrete floats in fresh water. If the bottom area of the boat is 6 meters cubed, how deep is the boat floating? Now, we know that boats are made out of things like steel and all that don't float. Normally, they have to be hollow in order to float. You can build a boat out of concrete. Matter of fact, there's a couple places around the United States where they have concrete boat contests every year. So, there's our free body diagram. We've got the water, we've got it sitting down in there. We know that it's a tie right now. Fg is equal to Fb because it's floating. The sum of the forces equals 0, so therefore Fg is equal to Fb. Now, we know Fg is 30,000 newtons, 3,000 kilograms times 10 meters per second squared. That's equal to the density of the fluid times the volume times g. Now, so 30,000 newtons is equal to the density of the fluid, which is 1,000 kilogram meters cubed. Sorry about the little mark there. Now, Volume, I'm going to make a neat substitution for volume. Volume for any material is found as area times height. Now in this case we're talking a rectangle, so it's length times width times height. So I'm going to put area times height in place of volume times g, which is 10 meters per second squared. I'm trying to solve for height. I know area. So therefore 3,000 newtons is equal to 1,000 times 6 meters cubed times h times 10 meters per second squared. H is equal to 0.5 meters. If somebody got in the boat would sink lower because Fg would go up. You would displace more fluid. Now let's do an apparent mass problem. We haven't done one of those in a while. 1 meter cubed of bricks has an apparent weight of 2,400 kilograms when submerged in salt water. In other words, that's how much it weighs when it's in salt water. What is the mass on dry land? Well, we know that salt water is going to provide a buoyant force, so the mass on dry land should be higher. So at least think that as we're going in, and then let's solve it. So if I draw my free body diagram, there's my blocks. Going down, I have the force of gravity. Going up, I have the buoyant force and that apparent force. Now, again, it's a force, so it's got to be in newtons. So the sum of the forces equals 0. So FB plus F applied, apparent, minus FG is equal to 0. Now, the buoyant force is equal to density times volume times g plus the apparent mass times g, which is going to give you the apparent force, equals Fg. Fg has simply moved over to the other side, and we know Fg is equal to mg. So now here's the nice thing is g is present in all of those variables, so I can get rid of g. So I get the density of fluid plus the mass apparent is equal to the mass on dry land. Well, the density of fluid is 1,025 kilograms per meter cubed. The volume is 1 meter cubed. They gave that to us. They also gave us the apparent mass inside there. And that's equal to the mass, so the mass is 3,425 kilograms on dry land. Now let's look at another one. A cube, and they give you the volume, is submerged in fresh water and attached to the bottom of a glass by a massless spring. If the cube weighs 10 newtons on dry land, what is the tension on the string? So we have something that looks like that. There's our cube. We have Fg acting down. We have Fb acting up. We also have tension acting down. And again, I'm guessing that it's attached to the bottom of the glass, so the tension would have to be tugging it down. So in this case, buoyant force is going to want to win, so it's going to try and pop out of the water if the string is cut. Now I'm going to consider up to be positive. My sum of my forces equals 0. So Fb minus Ft minus Fg is equal to 0. Again, Fb is going up, the other two are going down. That accounts for the direction. So I'm solving for Ft. So if I move Ft to the other side, I get Ft is equal to Fb minus Fg. Okay, now we're ready to start putting in things and solving it. Don't skip those early steps of the problem and try and go right to a solution. Think about it as, less chance of you making mistakes. So force buoyant, again, is mass of the fluid, density of the fluid times V times G minus M times G. So there's your volume, there's G. So that right there is going to give you the buoyant force minus the weight, which they gave us as 10 newtons. So therefore 1,000 times 0.002 times 10 is equal to 20 newtons. So 20 newtons minus 10 newtons. Buoyant force is 20 newtons. The weight is 10 newtons. So the string provides the other 10 newtons of force.